Karthik, and thanks for the introduction. And I must say that I attended my first Pyro Asia um, conference last year in Guwahati, and it was wonderful experience seeing that a lot of works happening in that area. And thanks to even Frontiers Lab, who is doing some great work and bringing academics and industries together, particularly for Asia region. Um, I think what I'm going to talk today is about my 10 years of journey in biosolids to biochar research and some of the lessons that we have learned in this area. Um, I'll start my presentation because I have this 10 years I need to finish in 30 minutes or 35 minutes. I might go a bit quicker. I'm just alerting you there, but I'm happy to connect with you later on and answer any of the questions that you may have. Or if you want to collaborate, more than happy to collaborate as well. So I'll quickly start with introducing my own group and the center that I'm leading here in Australia. My group is more looking at resource and waste conversion, more broader in the context. We look at biomass, plastics, and number of other waste streams. However, when I talk about biosolids, we have in Australia a national center on transforming biosolids, where pyrolysis is one of the alternative options we have heavily, comprehensively investigated. I'll talk about that a little bit, and then I'll talk about really our journey for the past 10 years, and then with some key conclusions and future recommendations, I'll conclude. Karthik, I'm just hearing some echo there. I'm not sure whether it's coming from any of our end. Okay, that's great. Okay, so I'm leading a group called Innovative Resource and Waste Technologies Research Group. So what we do is we take waste and resource and then try to convert them through biological, chemical, thermal, and mechanical processes into a high value materials. And we also work with engineers, scientists, policy people, even social scientists and the business people to translate and create impact of everything we do in waste and resource conversion. Um, our major area of focus is developing advanced thermal and hydrothermal technologies, also looking at high value material synthesis, nutrient and resource recovery, and also destruction and capture of emissions and contaminants. Our group has in the past 10 years received roughly around $44.5 million funding and several awards, and we're a large team. So this presentation that you see behind that, there are so many postdoctoral researchers and PhD students. We have also acquired now state-of-the-art IRWT pilot facility from industry and government funding, which acquires pretty much majority of the thermal and hydrothermal type reactors. And we're also now soon acquiring our first PyGCMS, and that micropyrolyzer is coming from Frontier Lab. We have some of the semi-pilot and pilot scale reactors in our lab, but also in field in operation in the area of pyrolysis and thermochemical conversions, both including pyrolysis, gasification, combustion, as well as hydrosolver thermal side. Okay, now I'll quickly talk about the center that we had. The center is called ARC Center for Transforming Biosolids, and it was a 5-year center. We just finished, but we had about $16 million cash from industry and our Australian Research Council, and we also have had a significant in-kind contribution from the industry. But we mainly focused on improving three themes, mainly improving technologies, enhancing product applications, and ensuring sustainability around biosolids. It is a truly national center. I'm just saying it was because we just concluded, but center is still in existence. We had pretty much all states were participating in the center activities. Now I'll start quickly with a biosolids fact sheet here. That what's biosolids, and it's very important for in Indian context or in Asian context first to understand and define biosolids, because biosolids could be way too different in India versus Australia versus any other country. So Australia mainly produce around 1.5 million tons of biosolids annually. In terms of volume, it equates to one full Melbourne cricket ground. So those who are cricket fans, you could appreciate that Australia alone just produces one full worth of Melbourne cricket ground worth of biosolids annually. We have around 1,200 small, medium, and large scale wastewater treatment plants. So biosolids produced in a very distributed manner. Positives of biosolids, they have good amount of macro and micronutrients, good for the soil. They also have good amount of carbon and other organic matters, so again, good for the soil. However, anything you eat, anything you drink, or anything that you even put on your face, everything ends up in wastewater treatment plants. So though biosolids have very good properties, they also have some of the unwanted products. For example, they have pathogens, contaminants, microplastics, pharmaceuticals, pesticides, heavy metals, and also they are very odorous. So, what we really felt 4 or 5 years back when we were putting up the bid for the Transforming Biosolid Center is that there is a clear need in the area of research and training around biosolids, mainly around improving technologies, existing technologies, or bringing new technologies, enhancing product applications from biosolids transformed products, and also ensuring environmental sustainability while we transform biosolids, maybe to biochar or any other product. Also, we felt there is a need for capacity and knowledge building, and also more integrated R&D type efforts, and also sustainable strategic partnerships in that area. What challenges we still find today relevant even after us concluding this center for after almost 5 years of work is that now biosolids land application is almost ceased in Australia, direct biosolids land application due to the presence of per and polyfluoroalkyl substances PFAS. So earlier biosolids were applied to agricultural land because of their macro and micronutrients and also organic matter. But as now they have this contaminant called PFAS, it's completely ceased. So here we have biosolids we can't apply to soil. There are also many other contaminants present other than PFAS, which are currently not regulated, but in future will be regulated. We also have shortage of landfilling and agricultural sites in close proximity to our wastewater treatment plants. So therefore, even if we find a way to put it back to the soil, I don't think all biosolids can be applied to agricultural soil. Also, biosolids management cost is very high, and we need to put efforts in future in reducing this cost. If we're going for biosolids to biochar route, then definitely cost of managing biosolids through pyrolysis process will increase. So therefore, cost-effective technologies are very critical for us to develop and demonstrate. Also, biosolids are very wet in nature, so they're about 10 after dewatering up roughly about 15% to 20% solids. So if you need to transport biosolids to longer distances, it could have higher transportation costs and associated CO2 emissions. So in this case, if you want to convert biosolids to biochar, you would need to do it more in a decentralized manner. So you might need more mobile plant or a smaller scale plant rather than one big centralized plant. And also, there is a negative public perception around biosolids. So even if you convert biosolids to biochar, people will still feel that, oh, you're producing biochar from poo. And they here in Australia, they have quite a negative perception about any product that comes out of biosolids. So we need to work on that side as well. Anyway, what my group did in last 7 years, we published around 42 papers in high impact journals. And if you look at how we have done publications is we have looked at the technology assessment and development side. We also looked at resource recovery and establishing some non-agricultural beneficial use type applications. We also looked at co-pyrolysis, soil remediation, again converting biosolids to biochar and put it back to the soil. And we also looked at PFAS management, particularly in biosolids via pyrolysis. So the questions that I'm going to really take you through very quickly what we have learned in last 10 years by answering these four key questions. So question one, how different is biosolids when compared to biomass and coal? Some of us might feel that, oh, this should be similar to biomass or coal, but when I go through slides, you will appreciate that biosolids are very different to biomass or coal. Then second question we try to answer is, how should we pyrolyze biosolids? What should be the pyrolysis reactor design? What we need in the front end and back end, and how we should integrate them to really pyrolyze biosolids more safely. Also, what applications we need to consider for biosolids derived biochar, particularly in non-agricultural sense, where we could apply this product. And also, how should we select technology for converting biosolids to biochar? Because there are 50, 60 pyrolysis technology providers out there. Which one to select for you? So um, what we have done is we started work back in 2015, 2016 with some laboratory studies or more field studies, but then eventually we also developed technologies, our own patented technology. So we've done series of studies. We have worked with industries very collaboratively, and done pyrolysis at multiple scales. So let me start with the question one. How different is biosolids when compared to biomass or coal? So to answer this, we first looked at the proximate and ultimate analysis of biosolids, three different biosolids, and compared them with biomass and coal. And as you would appreciate that biosolids is very different. They have very large, high amount of moisture, therefore very low solids content, compared to some of the biomass and coal. But importantly, after drying, even if you look on dry basis, the ash content in biosolids are much higher compared to some of the biomass and even some of the subbituminous coal. Volatile matters are somewhere sitting in the middle, but still lower than biomass and slightly higher than coal. Also, fixed carbon is very different, and they vary from different types of biosolids. So biosolids could be either produced from after dewatering. If you solar dry, that biosolids is called solar dried biosolids. If you have a drying pan, which is more clay containing, then those biosolids will be biosolids produced from clay lined drying pan. So they called clay lined biosolids, and also lagoon based biosolids, more produced from the lagoon based treatment plants. And if you really see at the bottom, the calorific value also significantly vary, and they are slightly lower than biomass, but significantly lower than coal. We also did a bit of a kinetic modeling studies. I'll quickly run through this just to so that you could appreciate the key message there. We tried to compare the activation energy of biosolids, solar dried biosolids, with different biomass and coal. And what we really found is that they are more in the range of biomass, but they are significantly lower than coal. So they could be pyrolyzed or combust because of their relatively moderate volatile content and a moderate calorific value. Their activation energy is in the range of biomass. We did some laboratory work just to understand, do they behave different to biomass? And yes, we observed that when you do a pyrolysis, slow pyrolysis in a laboratory setup, you clearly see the difference between the biosolids and biomass in terms of their yield, and then also oil and gas compositions, and also biochar properties. Biomass biochar are highly porous, while a biosolids biochar may not be that porous, given they have higher inorganic or ash content. Also, the amount of char you produce at the end will be much higher in yield compared to biomass. So there are significant differences there. We also try to understand that, because if you want to put these biosolids into any reactor, you want to understand whether that biosolids during the thermal treatment may attrit more due to thermal stress and some other form of breakages. And we did a bit of grindability studies for the biosolids in our lab, and we identified that biosolids actually have a relatively very high grindability index. That means they're going to attrit a lot more when thermal stress is introduced. Um, so they could generate a lot of dust, and then if dust is not handled well, you may have frequent shutdowns for maintenance of your pyrolysis plant. So they're not like coal pyrolysis plant or a biomass pyrolysis plant. Biosolids is very different, very fragile material, and will tend to produce a lot more dust. Okay, then second question we came on is how should we pyrolyze biosolids at scale? So that's where we started working at different scales in our laboratory, outside our laboratory with different plants, different scale plants. But before doing that, we just looked at we tried to compare the different reactor designs and really tried to understand that what are the key benefits with certain designs if you go. So majority of the reactors commercially available in the pyrolysis are either kiln or auger, paddle, or hearth type reactors. And if you look at in them, their bedside heat transfer coefficients range between 30 to 100 watt per meter square degree Kelvin. However, if you look at the conventional fluid bed pyrolysis, a conventional fluidized bed reactor, the bedside heat transfer coefficient could be at least double than what you could find in all these other reactors. And one of the reasons is why conventional fluidized beds are better is because they add a particle convection term in the whole equation, and that's why overall heat transfer coefficient on the bedside will always be higher. However, there are no currently commercially available fluidized bed pyrolysis process available, and there are several reasons behind it. Um, and one such reason is, if I like to quickly explain you, is that I don't know whether you can see me or not, but just imagine you have a cylinder in which the reaction is occurring, the pyrolysis reaction, and pyrolysis is endothermic reaction, so you need to provide heat to the reactor more in an indirect mode. And when you increase the cylinder diameter, the volume increases by diameter by square of the diameter, but the surface area only increases by diameter. And that's where, after certain scale, you will find that even fluidized bed can't provide enough surface area. So we've tried to overcome that particular limitation by converting conventional fluidized bed into a fluidized bed heat exchanger device. And it's RMIT patented process now. And we have done several scale demonstrations with this reactor. Um, it is first of its kind fluidized bed pyrolysis reactor. It can achieve much higher throughputs because it has higher heat and mass transfer. The whole reactor is made up of simply tubes and pipes, so it's like a fluidized bed heat exchanger, but it's just the heat exchanger type device. So you could easily fabricate and maintain that. It doesn't have any moving part, which you will have in auger, paddle, or multi-hearth type reactors, or even in kiln. So we hope that with no moving parts present, it will have a much lower maintenance cost and higher plant availability. And while designing our technology, we ensured that we offer flexibility to deal with feedstock seasonal variability in their quality as well. Anyway, I think I will skip this, how Pyroco works and all, because I have a lot to present. But I have presented this in the last Pyro Asia conference about this fluidized bed heat exchanger. But what we have done is we have successfully scaled this reactor. So we conducted a Mark 1 pilot trial. So this is what you see is a Mark 1 reactor, which is a fluidized bed heat exchanger. And then we have also now made a Mark 2 reactor. And we have done lots of trials. So we have almost uh, processed more than 10 weight tons of biosolids from 9 different wastewater treatment plants here in Australia. We have validated some of our claims that we made earlier in our patents, that we could achieve higher heat transfer and mass transfer. We could achieve energy neutrality. and we could also meet the staircase emissions requirement from the regulators. So all of that is done with the Pyroco. But more importantly, what I want to show you today is that what biosolids have and how any pyrolysis, not Pyroco. Pyroco may have some advantage in terms of its scalability and all that, but any pyrolysis you do would safely remove some of the contaminants. So what we did extensive studies on looking at the contaminants in biosolids and also in biochar through our pilot trials. So biosolids had a lot of pathogens in the beginning, probably, but once you dry it, those pathogens are gone. But we also didn't see any pathogens in the biochar at any temperature left over or regained. Then we looked at the heavy metals, and what we observed is that biosolids had all the heavy metals from arsenic all the way up to zinc, and their concentrations in biochar were mostly increasing for majority of these metals, and some of them were increasing to a level where even international biochar initiative guidelines, whatever they were proposing, we were well within that range, but still they were more for industry grade, so it can't still feed back to the soil because the concentrations are otherwise slightly higher than what you would need for any agricultural application. We also look at their leaching test, and we found that biosolids may have more metals leaching from them, but when you convert biosolids to biochar, their leachability goes significantly lower. That means that this biochar, when you apply to any application, the metals related contamination will be relatively less. We also looked at nutrients, because biosolids have very high amount of nutrients compared to biomass. Biomass doesn't have good nitrogen, phosphorus levels there, and also some of the micronutrients like sulfur and calcium. Biosolids have them in a great quantity, and we were able to retain majority of the nutrients, except nitrogen was 50% lost, but phosphorus was concentration was increased. And we did some work on biochar application to soil, and we found that if you use that as a phosphorus fertilizer, it can act as a very good slow phosphorus release fertilizer. We also looked at some other properties, and we found that all in all, compared to biosolids, biochar have better physical and chemical properties for various applications. We looked at some of the pharmaceuticals and personal care products that we use in our day-to-day life that ends up in our wastewater treatment and that hence in biosolids. They were all, majority of them were removed and destroyed at were removed at a pyrolysis temperature of 600. We also looked at some of the estrogens and endocrine disruptors that were present in our biosolids, and then at 600, they all were gone. Also, microplastics. So biosolids had a lot of microplastics present, and when you convert them into biochar, if you look at this FD's feed and then this is biochar, we found them mainly 90 to 99% removed, and still microplastics correct analytical methods for microplastics concentrations are still um, evolving. We also looked at the PFAS analysis in biosolids and biochar, and we found that a majority of the PFASs were safely removed, and we were not able to see any PFAS in our biochar produced from the Pyroco pilot plant. Then we did bit of a PFAS mass balance. So we looked not in only in the biochar, but we looked in the scrubber water that we produced from the pilot plant. And also we did the gas phase analysis. And then we looked at the overall mass balance. And with that, we found that biosolids pyrolysis process with thermal oxidizer at the back end could remove pretty much 100% of the, could achieve 100% of the PFAS destruction. PFAS is also very complex field, so there are so many PFAS and its precursors. So sometimes closing mass balance with PFAS is not possible. So we also looked into doing fluorine mass balance, and we tried to really get an answer whether PFAS is completely destroyed in biosolids conversion process to biochar. And we got some sense of idea that yes, biosolids uh, pyrolysis process, when it is integrated with thermal oxidizer, can completely destroy the uh, PFAS. Okay, then we also looked into what front end and back end technologies we would need. So biosolids, as I earlier mentioned, is very wet, so it will definitely need drying. But depending on your reactor type, you may need sometimes grinding, sizing, or screening units as well as pelletizing units, depending on which reactor design you choose. Um, and also at the back end, biosolids pyrolysis will need thermal oxidizer, because in pyrolysis you can devolatilize majority of the contaminants, but they may not be still fully destroyed. So you need to completely you need to combust these oil and gas vapors at much higher temperatures in order to destroy majority of these components. So again, in the back end you need thermal oxidizer, that's essential. And also along with that, for SOx, NOx, and PM removal, you need different other gas cleaning unit operations. With our Pyroco, we did comprehensive stack gas emissions analysis. We followed IED 2010 oblique 75 oblique EU standards there, and we were able to demonstrate that our trials were able to meet majority of the requirements listed in the standards. Sorry, I'm going, in the interest of time, I'm going quicker, but I'm happy to have a chat. Majority of this work is published as well, so I'm happy to share this. Okay, now then the third important question that we came across is that, okay, once you convert, you know that biosolids is not similar to biomass and coal, but now we know how we could pyrolyze biosolids. Then you end up with a product called biochar. Now, what do you do with this biochar? So mainly, if you could put it back to the agricultural side, it's good. But what if you can't put it into the agricultural side, given heavy metal concentrations are still very high in that biochar? So in that case, we may need to look for various non-agricultural applications. And we started with looking at the literature review on the potential applications of biosolids derived biochar, and we identified that there could be different 20 different applications, non-agricultural applications we could have when you convert biosolids to biochar. It could apply to almost 20 different areas. We also looked at some of the places where we could pretty much use our own biochar. So imagine wastewater treatment plants, they produce biochar, but then rather looking for external market, how about they find just some internal applications for the biochar? So that way they don't need to rely on external factors. And we found that way the biosolids could have many internal applications. First is, if you want PFAS to be removed at the influent level, you could sell your own biochar to your trade waste customers and ask them to install the biochar based adsorber units at their effluent treatment plant before it comes to the central effluent treatment plant. So biochar could be a good PFAS adsorbent. Then second, we thought we could also look at potentially use biochar as a removal or adsorption or recovery of ammonium from wastewater treatment plant. And also we could use it as an additive in anaerobic digestion process. Um, Adding biochar to anaerobic digester could improve biomethane potential by inhibiting ammonia release and a related stress on the methanogenesis bacteria. And also then we looked at how we could use biochar to remove some of the odors coming from the H2S. So that way, once you produce biochar, you could internally apply this biochar at a number of places within wastewater treatment plant. um, and avoid use of, they currently either use granular activated carbon or some of them very expensive media. So the point is that this way you could demonstrate circular economy, but also reduce the overall cost of the process. And also, we are developing a new technology for converting biogas to carbon nanomaterials and hydrogen by sequestering carbon from biogas. And that biochar could be a good catalyst for that biogas decomposition or biogas pyrolysis as well. Okay, so what we did is we did develop a Topsys based tool, and we put all these applications that we identified from our literature review, and then did the Topsys analysis, and then we kind of identified first top 6 applications where we could apply our biosolids biochar in Australian context. And based on that, we did various experimental work in our laboratory or at pilot scale as well. And we've published extensively in this area. So all these papers are published, and I'm happy to share. But some of the key findings are, for example, when we looked at biochar use for biosolids derived biochar use for nutrient recovery from wastewater treatment plant, we found that they are not as good as some of the cation exchange resins and zeolite. Those are commercially available. So you see biosolids biochar was just sitting here. But then we looked at some of the modifications in biochar, in particularly via very simple acid alkali pretreatment. And then we were able to enhance its cation exchange capacity significantly for our own biosolids biochar, and therefore overall adsorption capacity were now almost 60% of the commercially available resin. But understand that this resin costs $3,500 a ton, while this biochar with this added treatment would still be roughly around $1,000 to $1,500 a ton. So if you could use this modified biochar replacing resins for ammonium recovery, then it still makes a lot of commercial sense. Okay, so also we looked at the biosolids biochar as a catalyst for biogas pyrolysis, I would say, or biogas cracking. And we found that when we compared them with some of the synthetic catalysts, they actually perform quite well. And the reason why biosolids biochar perform good is because they have this heavy metals, some of the metals finely dispersed in biochar matrix, and if they remain active during the biochar conversion process, then they could act as a good catalyst. And that's what we're seeing, that they are available and active, and therefore they act as a good catalyst. Then we also looked at putting biochar with a very highly contaminated wastewater stream. So you could see the PFAS concentrations were very high. But then when we used biosolids derived biochar, we were able to remove majority of the long and short chain PFASs, though they were not as good as GAC, but they were still okay. So what it means that you might need to put a lot more biochar instead of GAC, but this biochar, if you won't produce on your own, then it would still save you a cost of bringing GAC to your site. So internal application for PFAS adsorption still makes a lot of sense. We also put biochar into anaerobic digester, and then we literally try to uh, um, look at how the biomethane potential increases. And if you see, compared to control where there was no biochar, when we added biochar or even alkali treated biochar, they both had a significantly higher biomethane potential. We also applied biosolids derived biochar more as an active electrode material in supercapacitor, and we found that with some modifications, you could achieve a pretty good electrochemical properties that could make it more favorable for its use in in electrode for supercapacitors and batteries in future. Also, we're currently looking at its applications into construction. And what one thing that we found, which is very interesting, is that you could use it as a replacement of cement, aggregate, or even admixtures type areas. But what we found is, cement is made up of literally lime, silica, and alumina. And if you look at what biosolids have, is they have this silica, lime, and alumina present in there. So essentially, they could be more, to me, looks like from the look of it, it's more like calcium, and then some silica there. So calcium and silica would put them somewhere in here. So they could more be used as aggregate kind of replacement, or they could be even when you have higher lime present there, they could be used even more as a replacement of Portland cement too. So the point is, we're currently looking at how these different types of biosolids could be used in different construction applications. And I forgot to add one slide here, but we have now made our biochar, uh, we have converted biochar into acoustic and noise barrier type panel. So we make, sorry, therm insulation panel. So we have acoustic panels, we have insulation panels. We could completely make it from biosolids derived biochar. Okay, we've also looked at H2S removal application using our biochar, and we compared that against literature. And you could see that when alone biochar won't work, but if you modify that with alkali treatment, then they could achieve performance at par with biomass or some of the commercial activated carbon. So the last point is that, okay, we have now demonstrated application of biochar as well. So we have solved how we can pyrolyze, how we could apply the biochar, and also importantly, first we understood how how different is biosolids compared to biomass or coal. The last answer is that now there are so many technology providers in biosolids pyrolysis area, or in general pyrolysis area. And how should water industry select a technology for converting their biosolids to biochar? And to answer that, we developed a tool called Biosolids Transformation Technology Assessment Tool. This tool is now getting commercialized in Australia. And there we have developed two basic criteria, two basic tools we called BETA's selection criteria based tool, BETA's SC, and then BETA's benchmarking. So where we can compare different technology options by doing a bit more comprehensive mass and energy balance as well as techno-economic analysis. So essentially, we developed this tool based on industry input, but also we derived a lot of correlations and empirical indices from literature review. So BETA's SC tool had a lot of factors we considered, and we kind of asked our industry partners to rank them according to their objectives. And with BETA's BM tool, we developed a comprehensive mass and energy balance model for auger type reactor integration, multi-hearth, rotary kiln, as well as conventional fluid bed, and the one which we're doing, which is more advanced fluid bed designs. So we developed comprehensive mass and energy balance as well as techno-economic analysis type tool here. So you could compare, more do apple to apple comparisons of different technologies. You would need a lot of data from technology providers for this, but once you have that data, then you could put in this tool and then generate a good mass and energy balance as well as the overall economic analysis. So what are the key conclusions? So biosolids are different to biomass and coal. Biosolids pyrolysis can safely remove contaminants, and as long as you have thermal oxidation post pyrolysis of biosolids, it will ensure destruction of contaminants. Biosolids derived biochar can have different potential non-agricultural applications, but some may need modifications. Techno-commercial viability of biosolids pyrolysis needs to be treated slightly differently. When you look at producing oils like SAF or something else from biomass, that's a completely different business case. But this is to me more like a technology that you are adopting to treat the contaminated waste. So it's more an environmental technology rather really making rather really looking at making significant revenue from this. So this is more to be treated by government regulators and water bodies, or any waste management companies, more as a uh, environmental technology, rather making a revenue generation stream, a technology which will generate additional significant revenue generation for you. Okay, where you could get benefit is if you demonstrate high value applications of biosolids derived biochar, then that could generate some additional revenue for you. But there again, you need to perform proper cost benefit analysis. You need to be careful in putting costs there, because you don't want to develop a business case with a very high end kind of a cost for biochar sale price, and then you know that market for biochar is still evolving, and it can be very volatile, so you don't want to really put all your investment by glorifying the biochar sale price there. So you need to perform this benefit analysis very carefully. Some of the future challenges, those who are still working in this space or want to work, where I think there is future research is happening, is probably pyrolysis technologies are still evolving in biosolid space, and there is a lot more to cover. Co-pyrolysis could be a next big topic. Siloxanes found in biosolids are one of those contaminants who could create a lot of downstream problems. More research needs to be done in the siloxanes area. PFAS and microplastics analytical and sampling side, still including their mass balance, still it's an evolving space. A lot of research still required in that space. And then um, new other emerging contaminants are coming, and then we need to keep checking whether we could safely remove and destruct them in the thermal oxidizer. So more and more contaminants are getting found in biosolids, and therefore this work will continue in that space. With that, I think I'll finish. Thank you all for your time, and I hope I have finished on time. Sorry if I've taken a bit more time there.
Yeah, Prof. Kalpit,